let's look at operational amplifiers, or as we said, op-amp. That's what we call them. That's more common name, op-amp. Operational amplifier. Now, first, the symbol we use for op-amp, you and I, when we draw them, we're going to use this symbol. It has two inputs and one output. That's the symbol we use. Normally, when you connect an op-amp, it doesn't look like this, by the way. It looks like a chip. Did you guys, any of you went to the lab with me for that digital logic when we did the op-amp? I mean, not the op-amps, and gates, OR gates and all that. They come on a chip. It has pins. So it looks like a chip like this with legs on it. That's what, and will be like 3, 4 of them on that chip there. And one of the things, you have to power that chip. So ideally, when you look at op-amp, you'll see, to make sure it works actually, will be a minus and a plus. I have to attach a plus, like a V minus and a V plus, and offset null. So you'll see some devices attached to here. It's called offset null. And you'll see a plus and a minus voltage. Those actually, plus and minus voltage, are important. And this is your V out. And this is V minus, this is V plus, that's coming in. You know, the voltage. These are your inputs right here. Couple of things to remember actually from this picture to that picture. That this voltage here, V out, will never exceed this number, and it will never be below that number. It's always between these numbers. So sometimes you can attach resistors to make the voltage 10 times bigger, 100 times bigger, but you will never exceed these values. Impossible. The way this op-amp works, if there's a plus 10 and a minus 10, that means V out between these numbers. If this is a plus 5 and minus 5, V out between plus and minus 5. You will never exceed these numbers. That's something to remember there when you build them, because mathematically I can make the voltage 1,000,000 times bigger by playing with the resistor. So if you put a 1 volt, get 1,000,000 volts. Well, trust me, it's not going to work that simple. Because if that's the case, we got it made. We can power anything from a simple circuit like this. You want 1,000,000 volts? Sure, I'll get you 1,000,000 volts. Put this resistor and put that resistor. But these guys says, oh, no, wait a minute. Your output voltage will never exceed these numbers. So if this plus and 5 and minus 5, you're stuck between these two numbers. We are going to be assuming we're dealing with ideal op-amp. So let me just write a few things about ideal op-amp. I'm going to just use this picture from now on. These are my inputs. And this is my output. I'm dealing with ideal op-amp. And one of the assumptions when it's ideal and op-amp, the first assumption is no current. No current ever flows into either input terminal. No current. What does that mean? That means the current going in here is 0. The current going in here is 0. By the same token, the current coming out of this is 0. The current coming out of this is 0. Nothing goes in. Nothing comes out of that end. Why is that? Because if this is ideal op amp, the assumption is that there's a resistor here, and the value of that resistor is infinite. Do we really get infinite resistors in real life? No. But we still make that assumption. It's not going to change our result by much. But we're going to make the assumption this is an infinite resistor. We have an ideal op amp. That means there's no current going in, no current coming out. That's the first assumption. Second assumption, there is no voltage difference. There is no voltage difference between the two input terminals. What does that mean again? If I call this voltage V minus, I'm going to call this voltage V plus. V minus has to equal V plus. Again, the reason for that, when you have an infinite resistor, what's the current going through it? 0. There's no voltage drop here. 0. This voltage equals to that. That's the reason. So these are the two assumptions. The current in equals 0. The current out, 0. This voltage equals to that. In real life, that's not the case. In real life, there's a little difference between them. That resistor is not infinite. So it might be 0.001 volt difference between these two ends. But the op amp has a gain usually. So V out, a lot of times in real life, it's some gain times V minus minus V plus. Or V plus minus V minus. The difference in the voltage. And that gain usually in the thousands, like 10,000, 100,000. So even if that difference is very small, notice I'm saying the difference here, 0.0001, 0.1 millivolt between these inputs. When you multiply it by 10,000, what do you have? You have V out to be 1 volt. If that difference was 0.001 volt, this will be 10 volts. But we're going to make the assumption, no, that's not the case. This is equal to that. The current going in equals the current coming out equals 0. These are the two assumptions I'm going to use for this chapter. I'm not going to be using that. So let's take an example, go through it and see what will happen. Here's a problem. Here's my circuit. This is attached to ground. V1 or VN we'll call it. And we'll call this V out. RF on the top here, we'll call it R1. I don't know. Just some different values. They could be equal. How are we going to solve this? Let's look at the second assumption, that there is no difference between the voltages right here and right there. If there is no difference, what's the voltage right here? This voltage. What is that equal to? As a number.
0.
Why 0?
Because if it's going in.
It's attached to ground,
voltage.
right?
Oh yeah, it's
Attached to ground. And if the assumption is correct, V minus equals V plus, that tells me V minus also going to be 0. So that's the first assumption. The second assumption, The current going this direction is what? 0. So let me define current going that direction. Current going that direction. Let me do KCL at V minus. KCL at this node. What is going in? Current going in. I don't know why I call R sub 1 instead of I. I sub 1, I sub F. I'm talking about the current through R sub F. What is the current going through that resistor? Or going into that node? Isn't that I sub 1? And what's the current leaving that node? Well, this is 0. There's nothing going this direction. I sub F.
That means the currents are the same.
Yep.
Equal, which makes sense.
Because nothing going in. So what is I sub 1? It's this voltage minus that voltage, V in minus 0 divided by what? R sub 1. And what's this one? 0 minus V out over R sub F. V in over R sub 1 equals negative V out over R sub F. I can multiply both sides by R sub F to get rid of the fraction. So I will have R sub F over R sub 1 times V in equals negative V out, or I can say V out is minus so this one actually will flip the sign. If it's a plus, I'll make it a minus because the minus sign. If it's a minus, make it a plus. Now just think about this. Take some examples. If we let R sub F equals R sub 1, what's V out? Negative, right? If we let R sub F equals 10 times R sub 1, I don't care what the numbers, but 10 times that number, what is V out? Negative 10 V in. If we let R sub F equals 1/3 R sub 1, what's V out?
Negative 1/3 V in.
Negative 1/3 V in. So we control what V out by changing the resistors, the two resistors. By taking these resistors and adjusting them, I can calculate how much voltage I want to get out of it. The sign is minus. That's the only problem. So let's say for the sake of discussion, you have a source here, a source. Let's think about this. I'll do a new source. You have a source of, here's a source of 20 volts. And somehow you have an amplifier here or speakers, and you only want to get 4 volts. You can't attach the 20 to the 4 volts. You're going to have a problem. We can use this amplifier to shrink that because this number is what? 1/5 of that number. So what I can do, I can take that 20 volt source here, attach it to an op amp, just like the one we just did here. Here's my 20. But now, because I want it to be what? 4 divided by 20. What's that ratio? 1/5? So for example, make that resistor 1,000 and make that 200. Is that 1/5 of this? The only problem with that, this voltage right here now will be what? Negative 4 volts. You say, well, I had my heart set up on 4 volts, not negative 4 volts. Somebody said, just flip them, flip the wires. I said, I don't want to flip the wires. I'll take another op amp. And make them equal values here. I don't know, 500 and 500. When these values are equal, the result of this is going to be the opposite to this. That will make it the plus 4 volts. And now I got the plus 4. I took the 20 volt source, fed it through both of these to give me the plus 4 volts at the other end. I can make it bigger, I can make it smaller. Notice when the resistors are equal, all you're doing with this circuit is just changing the sign. So by making these two resistors equal, I'm just flipping that sign from minus to plus. I could have used any resistor as long as they're equal. I could have used any values as long as this is what? 1/5 of that. So I look at my drawer, what do we have for resistors? Well, I got 1,000, I need 200. If I don't have that, I got 5K and 1K. Perfect, that will do it. Let's try another problem. And it doesn't matter if this is DC, AC, it will not change anything. Let's change the problem just a little bit here. Let's do this circuit. But instead of attaching this to ground, let's attach it to some source here, V. Vn. This is to ground. This is R sub 1. R sub F, and this is V out. Instead of the source being here, I put the source there. How is that going to change? So what's V plus? Vn, and since V plus equals V minus, that's Vn. Vn equals V minus. Okay. This current going in is what? 0. Let's call this current I1. Let's call this current I sub F. Again, KCL at Vn, at V minus, not Vn. Because otherwise, if I say Vn, you have no idea which one I'm talking about. At V minus, that's this node. The current in, which is I sub 1, equals the current out, I sub F. What is going in? 0 minus Vn divided by R sub 1 equals what? Vn minus V out over R sub F. Here, my LCD is going to be what? R1 RF. Two people out.
So what's with the R1 RF on the outside? Is that what we're multiplying it by?
Yep, that's the LCD. So when you multiply, you'll have what? Negative RF times VN equals R1 VN minus R1 V out. Shuffle things around. I'm going to bring this to this side. R1 V out equals R1 plus RF VN and what's V out now? R1 plus RF over R sub 1 times Vn. Now mathematically, let's see what will happen mathematically. If you play with that equation, let me write it down again. You can write that as what? 1 plus RF over R1 Vn. In the previous example, we managed actually to get the voltage below 1, right? Not assuming the negative sign, but the magnitude of it. Notice by playing with the resistors, where was it? Right here. I can make it equal. I can make it, don't worry about the minus sign, I can make it 10 times bigger. I can make it a third of that, smaller, with a sign. Tell us the difference here, this is always a plus. In term V out, always positive, not negative. This is always negative. But the value of this, V out, will never be below V in. So this case is impossible to get this number below that, because 1 plus that, even if I put a 0 on the top, if I put a 0 on the top, that says, oh, wait a minute, V out equals Vn. Anything bigger than that, this value will be bigger. So I can make it 10 times bigger, I can make it 2 times bigger, 5 times bigger, 12 times bigger, by playing with the values for actually R sub f and R sub 1. If I make, again, example, if R sub f is equal to 0, doesn't matter what R sub 1, that means V out equals what? Vn. If that's the case, I don't need an op amp. Just take a wire from this source, attach it to the other one. Attach it right there. If R sub f equals R sub 1, V out is going to be what? 2 times Vn. Because that'll be 1 here, plus 1, that's 2. If R sub f equals 10 R sub 1, V out is going to be what? If it's 10, that'll be 10 plus 1, 11 V1. If R sub f equals 1/10 of R sub 1, V out is going to be 1.1 Vn. So it's always equal to Vn or higher. It will never be below Vn. It's always positive. So if you're trying to shrink a voltage, stay away from this design. You can't. You will not be able to shrink it. You have to use the previous one. This is always going to be equal or larger. The only way it will be equal if this is 0. Any other number is going to make it larger. Let's try one more example and see. Different one. Make it a little bit more complicated. I'm just having fun here. That's plenty.
You have a very interesting definition of fun.
Fun, fun, fun.
How come they're all R's and not R1, R2?
I could. No, you want an R1, R2, R3? Go ahead. It's going to make the math ugly. That's why I made them R, actually. Just to make the math the LCD and all that.
Then leave it alone, leave it alone. I don't want to mess with that.
But if I did R1, R2, R3, your LCD becomes really ugly. So the math becomes, ugh. That's the only reason why I made them all R's. If we have some numbers like 10, 20, 30, the LCD will be a number, wouldn't be bad. But just to write R1, R2, R3, RF, multiply by that, it gets like, ugh, a little hairy. Okay, let's look at that. Let's go back to the basic assumption. What is V plus equal to? V minus, well, it's in terms of a number. What is that equal to? Zero, attached to the ground. So if this is 0, this is also 0. What else we know? What's the current going in? 0. So let's assign current in any direction you want. We'll call that I1, I2, I3, IF. KCL at V minus. What is going into that node? I1, I2, I3. What's leaving? IF. What's I sub 1? Yep, V1 minus nothing over R. What's I sub 2? Yep, V2 minus nothing. You don't have to whisper it. You can say it over R. What's I sub 3? V3 minus 0 over R. What's I sub F? 0 minus V out over R sub F. When Joe asked me why did I use R instead of R1, R2, R3, because I was thinking ahead. If I use R1, R2, R3, my LCD will be what? RF, R1, R2, R3. It makes it a little bit ugly. So I was trying to make it easy on all of us. Now my LCD becomes RF times just R. So if you multiply with that, you have RF V1 plus RF V2 plus RF V3 equals negative RV out. So that was my thinking about making them equal. They don't have to be equal, but that's why I was making them equal. I can factor RF out. V1 plus V2 plus V3 or I can say V out equals what? Negative R sub F over R times V1 plus V2 plus V3. This type of amplifier is called a summing amplifier because it adds them. A summing amplifier. It takes V1, add to it, V2, add to it, V3, and whatever the ratio of negative R sub F to R sub 1. So the value, if these guys are positive, V out is going to be negative because it's going to invert that signal. And if one of them is positive, the other two are negative, so it depends which one's bigger. But it adds the two of them. If the result is positive here, because the minus sign is going to make it negative. If the result is negative here, the opposite to that will be positive here. And the ratio is R sub F to R sub 1, or to R. Now, I forgot to give you names for the other two I put up there. The first one that we did remember this one? Look at your output. Negative R sub F over R sub 1 Vn. The negative, because of that negative sign, is called inverting amplifier. It's going to invert the signal. When it's plus, it makes it minus. When it's minus, it makes it a plus, like a NOT gate in digital logic. The other one we did, if you look at the answer, it's not inverted, so it's non-inverting amplifier. We call that a non-inverting amplifier because the result is positive.
The second one's the non.
Yep, the non-inverting. And this one we just did, that's called the summing amplifier because it adds all three of them. Is that this one? Yeah, the summing amplifier. I'll do a couple more examples here. I have time, maybe for two more. I'll make a short one. I like this one. It's one of my favorite. V in. This is V out. That's it. That's the whole circuit. Okay, if this is Vn, because that's attached to the ground, this is Vn. What do you think this voltage here? Vn. And where is that attached to? So what's V out equal to? Vn. That's it. There's no math, nothing. That's called a voltage follower.
So what's the use for that?
Voltage follower, it's like a unit gain. Two L's actually in follower. It's a unit gain amplifier. It gives you the same voltage as the source. You might say, then what's the advantage? Why not just attach this to the source directly? Well, if the source goes to 0, this one goes to 0. If you put an op amp, it takes a while for it to go to 0, so it gives you a little time. It's like a latch, a gate. Holds a little bit longer. But that's called a voltage follower. V out equals Vn. It's the same voltage. That's equivalent to attaching a wire right there. The only difference with the wire, once you change that number, this one changes immediately. Where when you have a gate like this, when you change the value, it takes a few seconds for it to see it, to go through it. That's the only advantage. It gives you a chance actually to grab it. It's like, for example, power failure. If you don't have a power supply right there or one of those backup, the minute the power goes off here, boom, your computer shut off. This one, the power shuts off, you have a few seconds for it, milliseconds or microseconds for it before you see it. Gives you a little delay there.
Like if the power comes off, would the gate be connected to like a battery or something like that?
Well, this one will not be used for backup because it's only going to give you like milliseconds, microseconds. So this actually used just to delay it so you get to see it. You'll see when we do digital, there's sequential design. You want a little delay for it to see it. So when the clock goes up, oh, I see the one there, let me grab that one there. But that's a voltage follower. Let me do one more. And this one, I'm going to modify the previous one a little bit there. Remember the summer when we had the summing amplifier? I'm going to make the resistors equal again for the same reasons I mentioned earlier, to make the math a little bit easier. This one. It's a little different than the previous one. No, not the previous, the one before that even. Where was it? It is different than this circuit. Notice the difference between them. The summing amplifier, this was attached to the ground, and all of these attached to that node. That's not what you have. First you have that extra resistor, so even if you erase it, it's still not the same because you want to attach this piece up there, because these guys were attached to that node. This one is not attached to that node, it's attached to this one.
What's this one called?
This one? I'm going to derive it, and you'll see from the name. Actually, it's called difference amplifier, but you'll see in a second why it's called the difference amplifier. Okay, we know there's no current coming out of this. We know there's no current going in that direction. Nothing. So really, you can just disconnect that if you want to. It looks like it's not there. Well, if that's the case, do we know what the voltage here? We'll call that V plus. Can we figure out what V plus is? Well, what about these resistors? Let's look at the circuit this way. Let's take a look at it this way. This is really what you have. And this is what V plus is. Because the rest of the circuit is not doing anything for you. This is what you have. Can you figure out what V plus is?
Just combine the resistors to get the current.
You can. Or why? Why not just voltage division? I mean voltage division. Voltage division is V2 times that resistor over the sum of them. So in this case, that's what? 0.5 V2, half of that. And if these numbers were different, that's fine too. Might be a third, a fifth, whatever the case is. What else we know? We know V minus is the same as V plus. So that's also 0.5 V2. So if we assign current going in the top node, we can say the current in equals the current out. And the current in, it's V1 minus 0.5 V2 divided by R equals the current out, which is this voltage minus that, over RF. Current in equals the current out. LCD to get rid of the fraction is what? RF. So RF V1 minus 0.5 V2 times R sub F equals 0.5 V2 times R sub 1, or R, not R sub 1, there's no R sub 1 here, minus R times V out. Let's combine all the stuff that we know. R sub F V1, bring this one to this side, minus 1/2 V2 R sub F plus R equals negative R V out. To solve for V out, you divide by what? Negative R. So what's V out? I'm going to write this one first. That becomes a plus 1/2 V2 times R sub F plus R over R. This would be a minus R sub F over R times V1. If you don't like the way I wrote that, you can write that RF plus R over 2R V2 minus RF over R times V1. That's what V out. That's why I said we call this difference amplifier. Now watch this. If I let RF equals R. What will happen? What's R plus R? 2R divided by 2R? 1. That'll be V2 minus what? V1. So that's where the name difference amplifier came in. It takes the difference between them. If you let R sub F same value as the other R's, you have V2 minus V1. It gives you the difference between the two numbers.